The next property can be stated as follows, and this has something to do with refinement of partitions. So first, we're going to say that Q is a refinement of P if P is a subset of Q. That is, that the partition P contains some points inside the interval AB, and Q will have exactly the same points in addition to more points. The following fact then is going to be true. So we already know from a previous item. In fact, I think my numbering is a bit off here, so this would be 2. And this should be 3. So the following is true. We already know from the previous item that L of Fp is less or equal than U of Fp, right? Any underestimation or lower Darboux sum is less or equal than overestimation of the same partition or the upper Darboux sum. And now we're talking before about the fact that when you refine the partition, then your underestimations will have to go down and your overestimations will have to go up. So for the refined partition, so for P, right, the statement that I just written is true. And exactly the same statement is true for Q, because Q is just another partition of the same interval. And so when we're refining, the overestimations will have to go down. So U of Fq should be smaller than U of Fp, right? Because Q is a refinement of P. And likewise, underestimations will have to go. Underestimations will have to go up, right? Underestimations become more precise, right? So they have to get closer to the actual value, so they have to increase, and overestimations will have to go down. So again, if we're talking about the upper Darboux sums, our upper Darboux sum of a refinement is smaller than the upper Darboux sum of the original partition, and the lower Darboux sum is larger for the refinement. So the middle inequality, again, is already true for all partitions, and we have established it. And we only need to prove either this inequality or that inequality, the comparison between two different partitions. And the proof is going to be virtually the same for both, so I'm going to prove this one, and the other one will follow in the same way. So we only need to prove that U of Fq is less or equal than U of Fp. Okay, so let's try to do this. Because P is contained in Q, and both partitions have finitely many points, what we can do is we can consider that Q has exactly one more point, than P, and then using induction. Right, so you're just assuming that Q has one more point, then Q has two more points, then Q has K more points, and from that, the argument should be true for K plus one more points. I'm not going to actually prove the induction here. I'm simply going to prove this fact for Q that has one more point, and then induction can be trivially used to prove the rest. So let Q have one more point than P. So let's say P is A equal to T0 less than T1 less than some Tk, etc. less than Tn that is equal to B. And Q has one more point, and let's suppose that the one more point is going to follow the point Tk. So actually let me change the notation for P a little bit. So less than Tk plus 1, because I'm going to assume that that extra point lies between Tk and Tk plus 1. So Q is going to be, once again, A equal to T0, less than T1, less than, etc., less than Tk, but now there is an extra point, let's call it C, between Tk and Tk plus 1. And so now, because there is one extra point in this, the last point is going to be still Tn equal to B. Right, so but overall in Q, there are n plus 1 points. In P, there are n points. All right, so then U of Fp, by definition, is a sum n from 1, k from 1 to n of capital M f Tk minus 1 Tk, right? Suprema over the interval, over intervals Tk minus 1 Tk times Tk minus 1. And U of Fq is exactly the same sum, except that we have this again, one extra point. So up until the point T actually, let me do one more change here. I'm going to call this Ti. Up here. So when k goes from 1 to I, right, we're going to cover these intervals in Q. So I have the sum k from 1 to I, m f t k minus 1 tk times tk minus tk minus 1. Right, so we have that. Plus, then we have two more intervals. One is from ti to c, then from c to ti plus 1. So we take a supremum over f, over the interval from ti to c. Times c minus ti. Then the next term is going to be coming from the interval from c to ti plus 1. So plus m of f c ti plus 1 times ti plus 1 minus c. And then there are more intervals starting from ti plus 1 and ending at tn, right? So plus a sum. So the next interval is from ti plus 1 to ti plus 2 that I did not take into account. So that means that we need to start from k equal to I plus 2 and end at n, and then capital M f tk minus 1 tk times tk minus tk minus 1. So I hope it's clear what I'm writing here, right? So again, what is my Darboux sum? It's a sum over all intervals where I multiply the length of the interval by the corresponding supremum, by the corresponding capital M. So I have to take into account the intervals from t0 to ti, that comes from here. I have to take account all intervals starting from ti plus 1 to tn. That is, so the first interval that I will see is ti plus 1 to ti plus 2. So if I start with k equal to I plus 2, then the first interval is ti plus 1 to ti plus 2, so that's exactly right. And again, I have supremum times the length of the interval. And then two extra intervals that I have not accounted for, that are kind of special because they involve this letter c in them, is an interval from ti to c, right, up here, and the contribution from the interval from c to ti plus 1 there. Okay, so now let's evaluate what we get for u of fq minus u of fp. And to do this, let me write u of fq in a slightly different way. So this summation from I to n, I can split into three different pieces. So I can go from 1 to I, oops. right? As my index goes from 1 to n, I can just choose to stop at I, right? All right, so then I'm going to skip k equal to I plus 1, right? If I want to. And after that, I'll have terms starting from I plus 2, k equal to I plus 2, all the way up to end, which is k equal to n. So plus sum k equal to I plus 2 to n mf tk minus 1 tk tk minus tk minus 1. Okay, so I'm adding terms from 1 to I here. I'm adding terms from I plus 2 to n. And the only term that I'm missing is going to correspond to k equal to I plus 1. And I'm going to write it separately. So when k is equal to I plus 1, then this will give me m of f. Then what is the interval? It's k is equal to I plus 1. I plus 1 minus 1 is I. So ti plus 1 times the length of the interval from ti to ti plus 1. Okay, so if I write things this way, then that is basically exactly u of f p that I'm subtracting. So all of this, oops, I will have to subtract from u of fq. So u of fq minus that. Okay, and so now I recall what is u of fq. U of fq is a sum of 3 pieces. This piece, actually 4 pieces, but I'm going to consider the middle 2 pieces together. So these middle 2 pieces and then 2 sums, some here and some here. And when I compare, the first sum is exactly the sum that I see, that I extracted from u of fp. And the second sum is exactly the thing that corresponds to the second sum in u of fp. So that means that this sum and that sum will cancel out because they appear both with a plus sign in u of fq and with a minus sign in u of fp. And so what's left is this one with a plus sign from u of fq, this contribution, plus that contribution, and from u of fp, this middle term remains, and it comes with a minus sign. So minus this guy. Okay, so which should be clear, right? Because partition P is basically exactly the same thing as a partition Q, except for the interval from tk to tk plus, or ti to ti plus 1 in P. In Q is being split into 2 pieces, right? And so then the difference between u of fq and u of fp is going to be the contribution from 2 pieces in Q, right? Minus contribution from 1 piece corresponding to 2 pieces in P. And I'm going to make one change here. So I'm going to rewrite this difference in the following way. I'm not going to do anything with the first 2 terms. But in the last two terms, I'm going to use it. In the last term, I'm going to use a telescopic sum as follows. I can write ti plus 1 minus ti as ti plus 1 minus c plus c minus ti, right? Basically adding 0. And then I can combine c and ti together and c and ti plus 1 together. Oops, to get ti minus c plus c minus ti. And because both of these terms are multiplied by this m, I can distribute to get the following. I'll have that, and then minus this guy times ti plus 1 minus c and then minus the same factor times times c minus ti, right? Times this guy. And so there is an equality sign here. Well, actually, there's no equality sign here, sorry. And so then I have two terms with a plus sign, two similar looking terms with a minus sign, and the only difference between them is this. So ti plus 1 minus c, another term with ti plus 1 minus c. C minus ti, another term with c minus ti. So I'm going to factor out c minus ti out of these two. That will give me m like this, minus this m, and both of these will multiply c minus ti, and then plus, now I'm considering these two terms which have a common factor of ti plus 1 minus c. So if I factor out ti plus 1 minus c, I'll have this m minus this m times ti plus 1 minus c. Okay, and so now let's think about what have we got here. So one thing that I can see immediately is this, that c splits the interval between ti and ti plus 1. So this guy, this difference is greater than 0, and likewise ti plus 1 minus c, that is also greater than 0, right? Because c is between ti and ti plus 1. And now looking over here, what do I have? I have at ti c is a subset of ti plus 1, right? Because ti is sitting in the middle. C is sitting in the middle of the interval between ti and ti plus 1. And likewise, c ti plus 1, for the same reason, is a subset of the same interval from ti to ti plus 1. And now, what is capital M? Capital M, again, is a supremum. And in part 2, we discussed that if I take a supremum over the subinterval, right, over the subset of the set, right, supremum over ti, comma c, versus supremum over ti, comma ti plus 1, right, tic is a subinterval of ti plus 1. So if I look at the larger interval, the supremum over the larger interval is going to be larger than the supremum of the smaller interval. And it's the same thing down here. C ti plus 1, right, is a subset of ti plus 1. So that means that the supremum over smaller interval is going to be smaller than the supremum over larger interval. So what this means is that this quantity is less than 0, and this quantity must be less than 0. Right? So therefore, by my observation from above, right, somewhere where it was this purple observation here, it follows that these differences are both less than 0. And that. Is also less or equal than 0. Okay, so what do we have then? We have that something which is less or equal than 0 multiplies a positive number. Something less or equal than 0 multiplies a positive number. Sum of two non-positive numbers is still non-positive. So this whole thing is less or equal than 0. And so that means that u of fq minus u of fp is less or equal than 0. U of fq is less or equal than u of fp. Right, and that's what we wanted to show. Okay, so that is then a lemma which allows us to establish the connection between upper and lower Darboux sums over partitions and their refinements, right? So if I'm refining my partition, then I'm guaranteeing that the upper Darboux sum is going to decrease and the lower Darboux sum is going to increase. Okay, next fact then. That would be the fact number 4. And the fact number 4 I can state in the following way. For any two partitions, P and Q of AB, we have that L of Fp is less or equal than U of Fq. Now, how does this relate to the previous result? So previous result was that if Q is a refinement of P, right, then L of Fp is less or equal, L of Fq is less or equal than U of Fp, right? So there was this chain of inequalities that we proved, but the important thing is that an upper Darboux sum of over P is going to be greater or equal than a lower Darboux sum over Q. And likewise, actually, an upper Darboux sum, the upper Darboux sum of F over Q from the same expression is greater or equal than lower Darboux sum over P. Now, why is this not really surprising is because, again, upper Darboux sums are overestimations of the area under the graph, and lower Darboux sums are underestimations. So if there is an area under the graph, then any overestimation should be greater or equal than any other underestimation. And so in 3, we're able to show that for two partitions where one is a refinement of the other. And in this item number 4, I'm saying that actually it doesn't matter which two partitions I take, L of Fp is always going to be less or equal than U of Fq. And likewise, actually, for the same reason, L of Fq should be less or equal than U of Fp, right? Because this fact must be true for all partitions, whatever. So let's prove this. Proof actually is going to rely on the thing that we just showed. And okay, so I cannot really compare U and L for partitions that are not refinement of each other. But what I can do is I can try to produce another partition which would be comparable to both P and Q. So somehow if it is a refinement of both P and Q, then maybe in that case I should be able to say something. So let's consider the partition let's call it T equal to P union Q. So T consists of all partition points of P and Q, right? So again, I'm writing T as a union of P and Q. I'm just indicating that T consists of all partition points of both P and Q. So then, well, P is contained in T and Q also is contained in T, which means that T is a refinement of both P and Q. And therefore, by the fact that we just proved, what do we know? We know that L of P of Fp right, must be less or equal than L of Ft less or equal than U of Ft less or equal than U of Fp, right? Because T is a refinement of P. And in the same way, T is a refinement of Q, so the same sort of chain of inequalities is going to be true for Q. Right? But if this is true, then let's see. So then if I look at L of Fp, right? And I follow this inequality. This is less or equal than L of Ft, right? But then I go down. What do I know about L of Ft? Is less or equal than U of Ft, which in turn is less or equal than U of Fq, right? Because the inequalities in the middle on both lines are exactly the same. And so that means that, of course, L of Fp is less or equal than U of Fq, right? Or by the transitive property of comparison. And starting from down here, I have that L of Fq is less or equal than L of Ft, less or equal than U of Ft. But then I can jump up, and I know that U of Ft is less or equal than U of Fp. And so again, by the transitive property of comparison, we have at L of ordering, right? L of Fq is less or equal than U of Fp. Okay? And so that is the proof of the fact that I just stated. Proof of the statement number 4. Any Lord-Darboux sum is less or equal than the upper Darboux sum, less or equal than any other upper Darboux sum. Okay, from that I can actually discover the next property, which is kind of obvious still. So if I have my upper Darboux sums, that they are always larger than the lower Darboux sums, and upper Darboux sums are overestimations of the area under the graph of the function, and lower Darboux sums are underestimations of the area under the graph of the function. So that in principle should mean that infimum of lower Darboux sums should be less or equal than the area under the graph of the function, and supremum of the lower Darboux sum should be less or equal than the area under the graph of the function. So supremum of underestimations should be no larger than the actual quantity, and likewise the infimum of overestimations should be no larger than the exact quantity, which means that infimum of overestimations should be larger than the supremum of underestimations. And so then we can express what I just said in the following way. We have that what was the supremum of underestimations? I call that the lower Darboux integral, L of f. And what is the infimum of overestimations? I call that the upper Darboux integral of f. And I expect that the following inequality will hold always. Remember that if two things are exactly the same, if the upper Darboux integral is equal to the lower Darboux integral, then your function is Darboux integrable. But whether or not they are integrable, this inequality should always be true, that lower Darboux integral should always be less or equal than the upper Darboux integral. Let's prove this. So, proof. I'm going to choose any partition P of AB. right? Then by the previous result, for any partition Q of AB, we have that L of FQ is less or equal than U of FP, right? Okay, but then U of Fp is a fixed number, and L of Fq, right, is a number that depends on a partition Q. And so then from this, I can conclude that U of Fp actually is an upper bound on all possible L of Fq's, right? And so therefore, supremum over all possible Q's of L of Fq, the greatest lower bound on L of Fq's, the least upper bound on L of Fq's is less or equal than just an upper bound U of Fp, so least upper bound should be less or equal than just an upper bound. So this is less or equal than U of Fp. But who is the supremum over all Q's of L of Fq? That's precisely the definition of L of F. Okay? All right, but then my partition P was chosen arbitrarily. And for any other partition P, exactly the same statement is going to be true. So therefore, L of F is a lower bound on U of Fp. And therefore, the infimum over all possible P's of U of Fp, which is the greatest lower bound, right? That greatest lower bound must be greater or equal than any other lower bound. So this should still be true. But what's the infimum of U of Fp's? That is, by definition, is my upper Darboux integral U of F. So L of F is less or equal than U of F, and so we're done here. That property has been proved. One last property that I want to show today, property number 6, that is going to be called, it's going to have a name, and it's going to be called the first criterion of integrability. And it's going to be stated as follows. Suppose that for any epsilon, greater than 0, there exists a partition P epsilon such that U of F P epsilon minus L of f p epsilon is less than epsilon. If this is true, then f is Darboux integrable on the interval AB. So if I want to show that my function is Darboux integrable on the interval from A to B, the only thing that I would need to check is that this statement is true for any epsilon, that for any epsilon, I can find one partition like this. All right, so let's see how we can prove it. So suppose that what I'm assuming here actually is true. Sorry, some rearrangement. And so what I need to show is that my function is Darboux integrable. So what does it mean? It means that for a function to be Darboux integrable, I need u of f to be equal to L of f. So what we need to show is that L of f is equal to u of f. And one thing that we already know, right, from 5, that L of f is always less or equal than u of f, right? And so then it would be enough to demonstrate that the opposite inequality also holds, so that u of f is less or equal than L of f, right? Because if that is true, then we're done. Okay, so then we already know, right, that such a partition P epsilon exists, that this is true here, right? So by our assumption, there exists a partition P epsilon. In fact, already the partition. Such that, and I'm going to slightly modify the expression above, such that if I add L of f p epsilon to both sides, I know that u of f p epsilon is less than L of f p epsilon plus epsilon. Correct? All right, so and then one more thing here. What about L of f p epsilon? If I take a supremum of L of f p epsilon, I'm going to get L of f, right? So that means that actually an L of f then is a greatest is a least upper bound on L of f p epsilon. So this is going to be less or equal than L of f plus epsilon, correct? So again, L of f plus epsilon is larger than L of f plus p epsilon because L of f is an upper bound on L of f plus p epsilon. And so then L of f plus epsilon is going to be an upper bound on U of f p epsilon, right? And from that, I can conclude, so from that, I can actually conclude one more thing. What is U of f versus U of f of p epsilon? U of f was the infimum of U of f p epsilon, so that means that this actually is greater or equal than U of f, right? The upper Darboux integral is the infimum of U of f p epsilon, so infimum is greatest lower bound, but it's a lower bound, so that means that there is this chain of inequalities that connects U of f and L of f. Now, p epsilon exists for any epsilon, so this statement then is true for any epsilon. And so now, sending epsilon to 0, right? So I can make epsilon as small as I wish here. We have that U of f must be less or equal than L of f, right? So right now, for a fixed epsilon, L of f plus epsilon is greater than U of f, but when I'm taking a limit, greater in principle can become greater or equal. So U of f is less or equal than L of f, and that's exactly the thing that I needed to conclude that U of f and L of f are the same, right? And so U of f is equal to L of f, and f is Darboux integrable on AB. And so we're done. Okay, so next time I'm going to prove an additional criterion of integrability and show that Darboux integral and Riemann integral are one and the same. And then after that, we will prove some known properties of definite integrals that we already considered in Calc 1. Okay.